Now what we can do is to rearrange, so we have this on the left side of this equation. And this is what we are doing here. We have in the output, and then we get all these other values here. So now what we are going to do is we are going to analyze these difference equations when our signal x is the unit step, and we will assume the initial conditions to be equal to 0. So we want that our output is 0 when Tn in this case is 0, and that the previous inputs outputs are also 0. So when we replace by n is equal to 0, we know that the output is 0. When n is equal to 1, and then we will have that this if x of 1 is 1 and x of minus 2 is 0, so we will have this factor here, which is present here, and then we will have that this is 0, this is 0, and we will end up with this here. So we have this divided by this. So when n equal to 1, we have this here. Then for n greater or equal to 2, so if we replace here by 2, we know that x of 2 is 1, x of 0 is 1, so this part disappears, and we will end up with y of n minus 1, and so this part here stays, and we have this equation for when n is greater or equals to 2. So now we have these equations, and we can implement an algorithm to generate a sine wave, so based on this recursive relation of the output with the previous value. So we need two previous values, so we don't depend on the output anymore, but we depend on n minus 1 and n minus 2. So now I want to use these equations to generate a sine wave. So the sampling frequency will be fs. We will generate 500 hertz with 1000, the amplitude equals to 1000. So here, as we mentioned, this t is 1 divided by the sampling frequency. And now we notice I'm defining here this coefficient. So a, I'm calling this is a, 2 times the amplitude times omega t. B, it appears here. So this is b is 2 times omega squared t squared minus 8. And c is this that appears here and appears here and appears here. So it's 4 plus omega squared times t squared. Now I'm defining y of 0, it's equals to 0. Y of 1 is a divided by c. So here I'm calling this is amplitude here, but a is all of this, c is all of this, so we have here. And then we will generate 1 second of a sine wave. So I will start by appending the output at time n equals to 0. Then I'm calculating the y at 2, n equals to 2, because we already have n 0 and 1. So after we calculate this, then the y0 in the next step, y0 becomes y of 1, and y of 1 becomes y of 2. So this is somehow we're using these recursion relations depending, so the future depends on the past outputs. So y of 2 depends on y of 1 and y of 0. So this is the recursion, and we update on the next step. So we will do this until we generate 1 second of a sine wave. For the implementation in C, we can further simplify the equations. So I will not use the sampling period, but I will use the sampling frequency. So I'm just replacing here. I'm not using omega, I'm using f. So which is omega is equal to 2 pi times f. So I'll be doing this. And also here I'm taking this out of this division, and we end up with these equations here. So this will make things a bit simpler. We must consider that we are dealing with 16-bit integers, and sometimes when we calculate powers it can overflow, so we need to be very careful on handling these situations. And of course we see that there's floating point mathematics here, and this will make the system to have higher computation demanding, higher computation power required. So usually in fixed point processors, when we have such floating point mathematics, it's emulated in software and it takes more time to process, but we don't have any huge tables stored in comparison to the lookup table. So we only have two values that are previously stored for our outputs, and we have these three coefficients that also needs to be stored. So this is now the generated sine wave, and we can also listen. So this is the 500 Hertz. The amplitude is equals to 1000. In this case, we need to see that the amplitude goes from 0 to 500. So is the peak to peak in this case is 1000 and not the peak. So we also need to take this in consideration when we implement this in our processor.